All right, folks, it's Bass Action back in action here. In this video, we're going to go through just a couple more examples doing an overall compare and contrast of our right triangle strategies. The first one we're going to look at is another application with our law of cosines. So we're going to take a look at this Major League Baseball diamond here. Okay, so we've got a Major League Baseball diamond. It tells us that it's a square that's 90 feet on a side. Now, we've actually already seen this general idea that the baseball diamonds are squares. So we're going to go ahead and just fill in these 90s here. And we're going to fill in these sides of 90. I didn't mean to do that one as a highlighter. There we go. So that's going to be 90. You could certainly put your other ones in here. They're not going to be as necessary for us. So we're going to fill in those as 90 on a side. It tells us that the pitching rubber, where the pitching mound here, is going to be 60.5 feet from home base. Okay, so this little segment here is going to be 60.5. Now, it is important to recognize that if this is a square, we do know something else in this figure. If we draw in the diagonal from home plate all the way out here to second base, it should bisect this angle. We've seen this when we did our proof of our 45, 45, 90 triangles. We should be able to recognize that that's going to be 45 degrees. Now, the reason that this is going to be really helpful for us is we're going to actually work with this triangle right here. So moving forward, the rest of the picture doesn't even matter to us. Now what we want to do is we want to start looking at what could we find in this triangle. Don't worry so much about what are the questions that it's asking. If we focus on this triangle, what do we know? What can we do? Is it a right triangle? Well, clearly not. Okay, we don't know anything that would indicate that it is. So none of our right triangle methods work. Do we know the measure of an angle and the measure of the side across from it? No, we don't. We're always missing something. So we're going to look at our law of cosines. And sure enough, if we are right here at this 45 degrees, we know the sides on each side of it. So we could solve for this x. So we can solve for this x, and that's actually going to be the distance from the pitching mound to third base. So that's going to let us solve for our first question. So we're going to use our law of cosines, and we're going to find a side. So we're going to say x is going to equal, and remember, we're going to give ourselves our big square root. If this is the angle we're at, we're going to put our piece fingers here and here on the 90 and the 60.5. So we're going to say 90 squared plus 60.5 squared, and then we're going to subtract 2 times those piece fingers. And then the last thing is the cosine of the angle that we're looking at. So we're going to say cosine of 45. I'm going to make my square root a little longer. Now, we're going to type all this into our calculator, and we're going to get that distance for x. That's our first answer, is going to be approximately 63.7 feet. Okay, so that's going to get us our first piece right here. I like to put this back into our picture. It's going to make it easier for us to understand what we're going to do for the last part. So the second question is asking us if the pitcher is initially facing home plate and they want to turn to third base, what is this angle that they're going to turn through to get there to throw the ball at third base? So we want to find this angle here. Now remember, we do not switch laws. If we started this with the piece fingers, we're going to end with that piece fingers. So now we want to find this angle. So if we want to find that angle, what we're going to do is we're going to set up our little angle formula, and we are going to say that the cosine of y, since we're looking for this angle, our piece fingers are going to go here and here. So we're going to say 63.7 squared, and the other piece finger of 60.5 squared. Piece fingers square and add together. And the denominator, we're going to multiply those piece fingers by 2. And then, of course, we have to subtract the square of the side across from it. So we're going to subtract a 90 squared. Now you're going to type all this into your calculator. Remember, that's going to give you a funky decimal. In fact, it's going to be a negative decimal. And then you're going to do your inverse cosine to get the measure of your angle y is actually going to be approximately 92.8. Now, I'm taking this one to tenths because this problem actually told us to take it to tenths. So we've now found both of our answers that we wanted to find. The last thing I want to do to end this chapter is to do a compare and contrast of exact methods and our approximate methods so that you can see that they are in fact the same. Okay, this is where we started the whole original chapter. This is where we were at in the very beginning, and we looked at this triangle and we said, hey, this is an isosceles triangle, so it's going to bisect the base, and it's going to make this side of the triangle 5 halves. We talked about not writing this as a decimal. We're going to do that as 5 halves. Then we're going to look at this triangle right here. And since it's a right triangle, we're going to do a quick Pythagorean theorem to find the height of that triangle. So we're going to say 144, I squared that 12, and then we're going to say 25 over 4. I'm squaring this side. I'm skipping that step because this should be a review problem for you, equals h squared. That means that our h is going to equal 144 minus 25 over 4. We've been here before. We're going to multiply the top and the bottom here by 4, and that's going to give us an h value of 551 over 4, where we had the square root of this and the square root of this. So this is going to become the square root of 551 over 2. Now that's the height of the triangle. So if this is asking us to find an exact, our area is 1/2. The height of our triangle is the square root of 551 over 2. And the base of the triangle is this whole side. That's a common mistake that students have, is they forget to do the whole base of the isosceles triangle, and that whole side is going to be 5. I'm going to put it over 1. Now we're going to multiply straight across, and that's going to give us an area of 5 times the square root of 551 all over 4. Okay, this is our exact area. Now what I want you to do is I want you to come over here and I want you to look and see, hey, what could we do over here if it only wants an approximate? Well, the triangle is not a right triangle, but what we do know is that we can easily find the measure of one of the angles in the triangle. I'm going to find the measure of this angle. So I'm going to say the cosine of x, and I'm going to put my peace fingers right here and here. So I'm going to say 12 squared plus 12 squared. I'm going to multiply them by 2 in the denominator. I'm going to subtract the square of the side across from it. And I'm going to get the measure of this angle to be 24 degrees. If I fill in this 24 degrees, what I can now see is that I have that lovely side angle side pattern that we have that great shortcut for. So now we can say 1/2 12 times 12 times the sine of 24, and we're going to get an area of approximately 29.3. Now, these don't necessarily look the same, but if you type this into your calculator, you're going to get the exact same thing as we have right here. So I wanted you to see that the exact methods and the approximate methods will get the same answer, but it depends on how the instructions ask you to write your answers.